Have you ever watched a satellite streak across the sky or a soccer player bend a free kick and wondered, how? How does that actually work? Well, the answer to pretty much every question about motion is found in mechanics. And don't worry, this isn't going to be some dry, dusty textbook lecture. I want you to think of mechanics as a user's guide, a practical toolkit full of powerful ideas that let us describe, predict, and really understand how everything in the universe moves.
So let's open up this toolkit. Here's our game plan. We're going to start with the absolute basics, the language we need to even talk about motion. Then we'll grab some predictive equations. After that, we'll dig into the why of it all with forces, analyze collisions using momentum, track the flow of energy, and finally, we'll figure out what makes things spin. Ready? Let's get into it. All right, tool number 1. First things first, right? We have to learn to speak the language. Before we can predict anything, we need a really precise way to describe what's happening. This is the foundation for everything else we're going to do. Okay, so right off the bat, there's this fundamental split in how physicists see the world. On one side, you've got scalars. These are just simple numbers, a magnitude. If I say I walked 5 kilometers, that's a scalar. It tells you how far, but that's it. But where did I end up? That's where vectors come in. Vectors have both a size and a direction. So saying I walked 5 kilometers east, now that's a vector. And trust me, in physics, that little bit of extra information, the direction, is an absolute game changer. So, building on that idea, our 3 most important words are all vectors. Picture yourself in a car. Your displacement isn't how far the road has twisted and turned, it's the straight line distance and direction from where you started to where you are now. Your velocity is just your speed, but in that specific direction. And anytime you speed up, slow down, or even just turn the corner, you're changing that velocity. And that change, my friends, is acceleration. Let's grab our second tool. And believe me, this one is a real powerhouse. If you know that an object's acceleration is constant, like a ball falling through the air, then these 5 equations, which we call the SUVAT equations, are basically your crystal ball. They literally let you predict the future of that object's motion. Okay, talk is cheap. Let's put this tool to work with a classic physics problem. We've got a stone, a bridge, and an inevitable splash down below. We want to know 2 things. Just how fast is that stone moving the instant before it hits the water, and how much time does it spend in the air? Now, before a physicist even thinks about formulas, they get organized. This table is the perfect example. We just list our 5 SUVAT variables. We know the displacement S is 50 meters. Since the problem says the stone was dropped, not thrown, its initial velocity, U, is 0. And because we're on planet Earth, the acceleration due to gravity, A, is a constant 9.81 meters per second squared. That leaves us with our 2 mysteries, the final velocity V and the time t. And once we're organized like this, the solution is just a 2-step puzzle. First, to find the final velocity v, we can pick the equation that doesn't involve time. V squared equals u squared plus 2as. We plug in the numbers we know, and we get a final velocity of 31.3 meters per second. Now that's over 110 kilometers an hour. Pretty fast. Next, to find the time t, we can use s equals ut plus 1/2 at squared. Again, plug in what we know, solve for t, and boom, the fall takes 3.19 seconds. It's simple, it's predictive, and it's incredibly powerful. So we can describe motion, and we can even predict it. But why do things move or change their motion to begin with? Well, that brings us to tool number 3, forces. This is where we learn the fundamental rules of the game, all laid out for us by the one and only Sir Isaac Newton.
These 3 laws, they are the absolute bedrock of mechanics. The first law is basically the law of inertia. Things like to keep doing whatever they're already doing. The second law is the famous F equals ma. It tells us that if you have a net force, an overall push or pull on an object, it's going to accelerate. And the third law, it says that forces are never lonely. They always come in pairs. You push on the wall pushes back on you with the exact same force, every single time.
And here's a really crucial point. Mass and weight are not the same thing. Mass is the amount of stuff you're made of. Weight, on the other hand, is the force of gravity pulling on all that stuff. So your weight is really just a perfect example of Newton's second law in action. Weight equals your mass, m, times the acceleration due to gravity, g. Okay, so forces explain how things change motion over time, but what about really sudden, really intense interactions, like car crashes or billiard balls colliding? To analyze those kinds of powerful events, we need to pull out our 4th tool, momentum. This is the key to understanding impacts. The idea behind momentum is beautifully simple. It's just an object's mass multiplied by its velocity. You can think of it as mass in motion. A huge truck moving slowly can have the same momentum as a tiny car moving super fast. And don't forget, since velocity is a vector with direction, momentum is a vector too. And this is what makes momentum so incredibly useful. It's what we call a conserved quantity. In any closed interaction, like two things crashing into each other, the total amount of momentum in the system before the crash has to be exactly equal to the total amount of momentum after. Momentum can get shuffled around between objects, but the total never, ever changes. It's a fundamental law of the universe.
So, let's see this principle in action. Here's the setup. We've got a 500-kilogram car moving along at 4 meters per second. It's about to slam into a stationary 1,500-kilogram truck. After the collision, they stick together and become one big wreck. The question is, how fast is that combined wreck moving? And the answer is 1 meter per second. Now, how do we know that so easily? Conservation. The car's momentum to start was 500 times 4, which is 2,000 units. The truck's was 0 since it wasn't moving. So the total momentum before the crash is 2,000. That means the total momentum after the crash also has to be 2,000. The new combined mass is 2,000 kilograms, so to keep the momentum at 2,000, the velocity must be 1 meter per second. See? The principle does all the heavy lifting for us. Our fifth tool is maybe the most fundamental concept in all of science: energy. Honestly, the best way to think about energy is to think of it as the universe's currency. It's what you have to spend to make anything happen at all. It's the currency of change. Now, in mechanics, we're mostly dealing with these three forms. You've got kinetic energy, which is the energy something has because it's moving. Then there's gravitational potential energy, which is stored energy, like the energy an object has just by being up high. And finally, there's work done, which is just the energy you transfer when you push or pull something over a distance. And just like momentum, energy is also conserved. It's another one of those fundamental rules. Think about throwing a ball straight up in the air. As it leaves your hand, it has a lot of kinetic energy. As it climbs higher, it slows down, treating that kinetic energy for stored potential energy. At the very peak of its flight, it stops for an instant, and it's all potential energy. Then, as it falls, that potential energy converts right back into kinetic energy. The total amount of energy never changes, it just switches its form. We've covered things moving in straight lines, we've covered collisions, but what about spinning and turning? For that, we need our final tool from the toolkit: moments. This is what explains the physics of rotation, pivots, and why things either stay balanced or tip right over. A moment is really just a turning force, and to figure out how big it is, you just multiply the force by the perpendicular distance from the pivot point. It's the reason why using a long wrench makes it so much easier to loosen a stubborn bolt. You're not any stronger, you're just increasing the distance, which gives you a much bigger turning effect, a bigger moment. And this simple but powerful idea is the secret to all balance. For anything to be stable and in equilibrium, whether it's a couple of kids on a seesaw or a massive skyscraper, all the turning forces in the clockwise direction have to perfectly cancel out all the turning forces in the anti-clockwise direction. It's this elegant little rule that literally keeps the world's structures from falling down. And there you have it. The language, the equations, the rules of force, the secrets of momentum and energy, and the physics of rotation. This is the physicist's fundamental toolkit for mechanics. But it's more than just a bunch of formulas. It's a whole new way of seeing and understanding the world in motion all around you. So now that you have the tools, the only question left is, what mystery are you going to solve first?